Hello everyone, and welcome to another video about acquisition of electrophysiological signals. My name is Marija Novicic, and in this exercise I'll show you how to make a simple LabVIEW program for measuring impedance of the electrodes. In previous video, we show you how to make a basic data acquisition application. We're going to use that application as a starting point for today's lecture. Let's open this application and go to the block diagrams to see which elements we have there. So we have all the elements that are necessary for acquisition, that is create channel, timing block, start the acquisition, read the data, clear the task, and error handler. We already went through what physical channel means, rate of the acquisition, and the difference between continuous and finite samples during the acquisition. We said finite samples means that acquisition is going to last a finite number of samples that we set, and continuous samples means that acquisition is going to last until the program is running. Okay, so we're going to choose continuous samples. We have to add some more inputs to this create channel block, because we are going to measuring signals from the real AD card, not the simulated one. Okay, before we go through that, I'm going to start the Emacs so we can see the difference between real and simulated AD card. In the devices and interfaces, we can see which cards are simulated, which cards are connected, and which are not connected. So this device 2 is simulated because it has a golden USB sign, and device 1 and device 3 are real but not connected AD cards because they have this black USB sign with a red cross on it. When we connect the device, we are going to have only the black USB sign. Okay, I'm going to close the Emacs and go back to the application. So, because we're measuring from the real AD card, we have to say which is the maximum value of our that our input can take, which is the minimum value, and what is the input terminal configuration. Input terminal configuration specifies how we measure the signals. I'm going to place a constant here so we can see what are our options. Okay, so we have default options, and let the program decide which measures is running. So we don't want that. We want for us to tell the program what are we measuring. And there are RSA options and differential options. So RSA means reference single-ended, and it measures a signal that comes to analog input relative to the ground. Differential means that we are measuring the difference between two signals that are connected to the plus and minus sign of our analog input. Because we want to measure RSA that is relative to the ground, we are going to select that options. For maximum value, we are also going to set control, so we can change that on our front panel. And for minimum value, we are going to set a control also. Okay, so I'm going to save this with another name so we know that is for electrode testing. So it's okay, so we have another copy of that program. Next thing to do is to program our application. Before we start programming, we'll have to see how our circuit looks like. So I'm going to open this picture, and this picture shows us that we have generator, unknown impedance, and known resistance. And we're measuring the voltage at the input of the circle and voltage at the output of the circle. And with some mathematical equations, we are going to get the unknown impedance. We saw the circuit, so I'm going to quickly write the equations we're going to use. So R, that is the real part of our unknown impedance, is equal to R1, resistance that we know of, times sinus of theta, that is the phase difference between V0 and V1, times V0 slash V1 minus R1, the resistance that we know of. And unknown imaginary part of our impedance is equal to R1 times sinus of theta times V0 slash V1. Okay, this is cosine. I took a wrong function. Okay. Because we need both V and V0 and V1, I'm going to need here both of those signals, not the joint one. So I'm going to use index array function to collect that data, and this is V0. That is on the first row of the data, and I'm going to use the same function, only I'm going to select the data from the second row. Okay, now we have VA and VB as our outputs. I'm going to set this a little bit lower so we can put our code here. Okay, because we get VA as a number of samples, we're going to use root mean square function to calculate the mean value of our signal. So rems.vi, and I'm going to place that here and also here. Okay. Next, let's place some indicator of our voltage, so graph indicators. I'm going to open a front panel and copy this graph. I'm going to name this V0 and this V1, and disconnect these two, and this is V0 and V1 is this one. Okay. So how do we get our phase difference? I'm going to use a block that I made, it's called phase difference, and I'm going to show you how I code it. So our inputs are VA and VB, that is our V0 and V1. Also DT, that is period that we're going to use to calculate the fundamental frequency, and the output are that phase difference that we need and fundamental frequency. Okay, so what is fundamental frequency? That is the frequency at which is placed maximum of our amplitude magnitude spectrum. So if the maximum of spectrum, if frequency of the maximum spectrum for VA and VB is the same, then we are going to calculate the phase difference. In other case, we are not going to calculate anything. So we are taking this function that calculates minimum maximum of the array and compare it with the VB maximum of amplitude spectrum. When we know that frequencies are the same, we're going to use that so we can extract the phase from that frequency with index array function again. And when we do that for VA and VB, we can subtract those two values and get our phase difference. That angle can be anything, so it can go over the range from -pi to pi. So we're going to use this function to set it in that range. This function works that it takes one angle as input and has the other angle as output, and basically subtracts 2p, adds 2p until the value of our angle is greater than minus p, and then subtracts the 2p until our value of angle is larger than is smaller than pi. Okay. And as the output, we get our phase difference. With fundamental frequency, we have to set this index, that is 32 integer, to double value and multiply it with our delta frequency constant, and as the output we get fundamental frequency. Okay, so I'm going to close this. We placed it on our block diagram, and now we can subtract the VA and VB there. Okay, so let's make this a little bit nicer. I'm going to set this. Okay. Next, we are going to multiply that with R1 and V0/V1 for R and for X also. Okay, so we're going to need, first of all, sine, sine and cosine function, okay, for the phase difference, and the upper is sine function and the lower output is cosine function. So we are multiplying sine function with R1 and with the V1 divided by V, V0 divided by V1. Okay, so we're going to need divide function, because we are going to divide root mean square value of V0 and root mean square value of V1, and we're going to need compound arithmetics with multiply symbol at the output, and we are going to multiply this and sine for X. We're also going to need R1 we are going to place R1 as numeric control. Here it is. Okay, so that is that for the X. I think I inverted the... Okay, so create indicator X in ohm. Okay, and the R is equal to also compound arithmetics. We have R1 cosine of the phase difference and V0 divided by V1. We also have to subtract the R1, so we are going to use subtract function that we're going to connect to R1. So as the output, we get R in ohm. Okay. So we have our X, R, and we're going to set this fundamental frequency as indicator. I'm going to call it fund freak, so has less space, and here it is. Also, we are going to place this phase difference as the indicator also. So here it is. This is phase difference in radians. Okay, so let's set that here. Okay, I'm saved the application, and now we have all these outputs here. So X, R, fundamental frequency, and phase difference in radians. Okay, that was that for this application. See you next time in another example.
The previous video presented code programming for the application that could be used for the electrode impedance testing. Why electrode impedance is so important? The contact tissue electrode electrophysiological amplifier could be modeled by the schematic presented in this figure. It includes tissue resistance, half-cell potential, which originates from oxide reduction processes of metal electrolyte contact, then resistive and capacitive effects of electrodes, and resistance of the electrode conductor. An ideal interface of data acquisition system to the human body is the short circuit. However, high contact impedance could affect to the data quality. That is the reason why we have to check the impedance of electrodes and the overall impedance of the contact. One way to determine the unknown impedance is by using the electrical circuit presented in this figure. R1 is known resistance and Z is the unknown impedance. We have to measure voltage 0 and voltage 1 as it was shown in previous demo, and then calculate two components of the impedance, resistance R and reactance X. This video demonstrates testing the impedance that is pure resistance by the developed application. This video demonstrates testing the impedance that is pure capacitance. This video demonstrates testing the electrode impedance.